So my name is Tim Pasang. I am the department chair for engineering design and manufacturing department, and I also happen to be the chair for this presentation session. So this is our second presentation, right? The first one was great. This is also great, right? And let me ask you guys first, who are here to support? Oh, there's 6 of them, yeah? Okay, this group. Who are here to support this group? Pretty much everybody, yeah? Okay, good, thank you. Right? So we have people from industry, we have some alumni, we have current students, we have parents, right?
Husband.
Oh, husband, I'm sorry. Any parents here?
Oh, crap.
Any parents? No? Just a husband? Okay.
I have my students.
Student.
A student?
I have my
I'm
student
her
here.
student.
Okay. Oh, the student from
My
Kilo.
students.
I'm her student.
Yeah. It's my student.
I am her student.
Oh, really?
Yeah.
She is my professor.
Yeah.
Okay, good. Thank you, thank you. Right, so we have students
No,
and
here.
her students, right, and everybody here who actually come to support them. So we thank you and we appreciate your time and being here. Yeah. So let's just jump into the presentation. So there is Nick
Only 12
here,
years old.
Ivan,
Yeah,
Ahmad, Tiffany,
He was
Luis,
pointing to
and
me.
Ed.
He was
Okay.
pointing.
So guys, take over.
Well, we are designing, building, and competing a fluid-powered vehicle. Oh, louder. Hi. We're designing, building, and competing a fluid-powered vehicle. I am Tiffany.
I'm Ever Prescott.
Ms. Molina?
I'm Ahmad.
I'm Jeevan. And I'm Nick.
This project is part of the Fluid-Powered Vehicle Challenge, further known as FPVC. It is run by the National Fluid Power Association. The goal of the FPVC is to build a reliable vehicle that is run on hydraulic fluid power. It is about creating a innovative, efficient vehicle that works outside of the box. Our objectives were to design and construct a vehicle that is run on hydraulic power, and to participate in the National Fluid Power Association competition, which runs after we graduate in the last weekend of April, first weekend of May. And we need to ensure that it is fully compliant with the NFPA rules and regulations, including but not limited to the implementation of 2 independent braking systems, utilizing both direct propulsion and regenerative braking, and a maximum weight of 210 pounds. So, what is a hydraulic system? I have a little video for you. It runs? No? Okay, so. There you go. So, we start with the pedals. The pedals are going to start the power. We go from the fluid tank down to our pump. The pump is going to move that energy into our motor as well as into our accumulator, where it is going to build up pressure. The pressure then can be released into the motor, and the motor is going to move this back wheel, which is going to power the whole bike forward. We started this project by working on our initial ideas. We threw out a bunch of ideas and we drew up some sketches for some of them. And we used our engineering design process. So we started with our problem. What is the problem? We want to make a hydraulic powered vehicle. So we started brainstorming, and I am going to turn you over to Aman, who is going to discuss how we made a decision on what vehicle to choose.
Thank you. So after the initial idea was drawn and presented in front of the professors and among the teammates, we decided that the tricycle and the tricycle recumbent was 2 great options for our project. But to finalize which frame would be best for our project, we had to make a few metrics which helped us determine which bicycle frame would be best for a project. As you can see on the left is the attributes that we took into considerations while determining where top being the most important attribute to bottom being the least important attribute. And based on the scores that we provided, considering these attributes, tricycle recumbent was a great choice for us. And as you can see, the tricycle recumbent, we chose the design, and after the frame selection was done, hydraulic circuit was something that we need to work on, and Ed is going to talk about it.
So simultaneously to the working of trying to figure out what kind of frame we wanted to work on, we started working on our hydraulic circuit. Starting out basically was just figuring out, went back to the key problem of what do we need our circuit to do. Like the most simple circuit would simply just be having a pump that drives to a motor, which then just returns to the reservoir. Simple as that. But because of the problems we had to meet, given the challenge of the competition, we then had to modify our circuit into this very complex multi-valve, multifunctional system. So listed are all of the different components and parts that we had to use, the pumps, the accumulators, the motor, all the things Tiffany was talking about to make our circuit work. So using this system, we were able to get these modes of operation. We have our cruising mode, which is just our simple operating, moving forwards and backwards. We have our coasting, which is just simply if you've got a hill and you want to take a rest, because I can tell you it's hard to pedal. We have accumulator discharge, which is when we have stored up energy, such as when we have our regenerative braking, we need to release that energy back into the system to move ourselves forward. We then have for preemptively before the competition, it's split up into 3 races: a top speed, efficiency, and a endurance race. You're allowed to charge up preemptively, so we had to make sure we had that option going into the thing of getting our accumulators charged up for our races. So from there, as you can see, this is a very complex multi-valve, a lot of parts going on. We were able to work with SunSource to simplify it down into a manifold system. So we're able to eliminate a valve and to take what was that huge complex tangle of hoses and tubing and condense it down to, on the back of our bike, we have just a block of aluminum. That is our manifold. That is what allowed us to get rid of a whole lot of joints, a whole lot of leaks, and a whole lot of headache, and just turn it into that one simple component. It is made out of 6061 aluminum. It is highly corrosive resistant to make sure no oils, grease, whatever things we dump on it. We have dumped a lot of oil on it accidentally. It's just part of the process and all the learning. The way it actually works is then the electronics in the system. There are solenoids which have an electronic current. Mounted behind the seat is a small battery which is 12 volts. Each of the solenoids, as built, can be controlled by the controllers. Those in the front can see the blue lights. Those in the back, you'll have to come take a look at after the competition. There's an extra switch in our controls you can see in the photo that is not lit up right there. That is actually preemptively in the fact of going forward. Right now each switch controls one of the 4 solenoids, but we hope to change it over to each mode will be controlled by a switch. Rather than having to know I need, solenoid 1, 3, and 5 activate, or 1, 3, and 4, I will just say I need to turn on, cruising mode. I'll just hit switch 1. So that is what we're hoping to move forward to. I will now pass the presentation over to Luis. We'll go over the kinematics.
So in order to make sure that the system worked and was functional for the competition, we could have approached it in 2 different ways. Firstly, it could be approached through the pedal speed of an average human, which is around 40 to 70 RPM, or through the expected speeds that we wanted the vehicle to achieve, which were around 10 to 14 miles per hour. We decided to go the route of going through human powered, as the vehicle should be able to be pedaled. And as such, we decided to go around starting with the pedal angular speed, then calculating the speed that we will obtain from that angular speed, given our ratios. After that, we consider the horsepower being in between 0.4 and 1.0, which is the general horsepower a human can generate as a control value. From that, we apply the gear ratio that we obtain for the pedal pump ratio, which is a total gear ratio that we obtain from the gears that we installed into the system, and from that we calculate the pump angular speed from the pedal power speed, from the speed that we get from the pedal speed that we got here, and the pump pressure from the pump angular speed, which at the end of the day give us the minimum and maximum flow rate, which take into consideration the horsepower generated by the human. After that, we take into consideration the motor wheel part of the system. Since both systems are connected by the same through the same kinematic system, the flow rate remains the same. And the speed also remains the same because that's the speed that we're taking that's the speed we're taking into account, and the speed that we're taking that we're pedaling with. As such, we take into consideration as well the wheel radius of this system, which is 0.79 feet or 19 inches. No, 9.5 inches. And after that, we calculate the angular velocity through the gear ratio over here. We calculate the angular velocity of this of the system. Then with the gear ratio we have on the back of the wheel, which is 1.867, we calculate the motor angular velocity, and from that we obtain our final motor torque and the final power output, which in a rest scenario is 0.95, and at maximum is 1.59. And after that, I'm going to pass it over to Nick.
So after finalizing our kinematics and hydraulics, we could start working on our CAD assembly. So to start our CAD assembly, we decided to use SolidWorks because most of us know how to use SolidWorks in this group, and we were just most efficient with SolidWorks. And the bike design really helped us with locating a lot of our key components, because we have a lot of hydraulic components that need to be located in certain spots, and it helped us with locating, not only just visualizing the bike, but also coming across a lot of clearance issues, assembling the bike, and then also fabrication. So now moving on to the pump support. The pump support we decided to place closest to the pedals, right here, and the reason for this is because it's just the simplest option, and it's the least power loss, and it's just got the it's closest to the pedals is just better. Now our gear ratio for this was pretty high. It's 20.4 to 1. So in order to achieve this, we had to do a 2-stage drive system. So to start with this, we decided to go from the pedals, a gear, coming off to another gear, to the jack shaft. And the jack shaft is right there in blue, and on the other side jack shaft is a sprocket and chain, located green and yellow. And the sprocket and chain then goes to the pump shaft. To get an example of what 20.4 to 1 gear ratio looks like, it's about every 1 rotation of the pedals is 20.4 rotations of that pump shaft. So now moving on to the motor support. The motor support is located in the rear, next to the rear wheel. We decided to place this right on top of the rear axle because it's going to be a straight gear connection, and this is very easy because we have a 1.81 gear ratio. So what that looks like is every 1.81 turns of the motor shaft is 1 rotation of the wheel. And this is just the simplest for maintenance, efficiency, and being able to design the bracket. Now moving on to our overhead support bracket that we designed. Now this bracket is probably one of our most important parts because it doesn't just serve one function, it serves a few different functions. The first one that we first wanted to design it for was to stabilize that motor support bracket. As you can see right here, it's connected on the top, giving the motor support now 2 points of contact to withstand a lot of the torque that the motor would be giving off. And that helps keep it sturdy as well as keeping the gear aligned. And then the second function we wanted to serve was to hold our manifold, which is located here on top in blue. And this is basically the heart of our fluid control system. So now I'm going to move on to Tiffany, and she's going to talk about some of the FEA that we did.
So our FEA is our finite element analysis. We wanted to make sure before we manufactured these parts that they were stable enough and would handle the amount of torque we were going to place on them for our bike. So we made sure to run an FEA analysis on each of the parts that we made in-house or elsewhere. So we ran an FEA on all of our parts, but I'm showing you 2 because we do not have time to go over all of them. This is our pump support and our motor support mount. And you can see that both of them were well over our safety numbers. I used the torque that Louise found for us, as well as our maximum PSI for our pump over here, and the weight of both the motor and the pump went into the analysis. And these numbers might not mean anything to you, but the deformation that could be caused from any weight or torque or movement caused from the action we're putting on our bike through is less than the thickness of a single human hair. So, well within our safety standards and factors. So now we are going to Aman, and he's going to tell you how we made all of these parts.
Sorry for that. And so here is just a CAD drawing of all the fabricated parts that we fabricated at the Western Michigan Student Machine Shop. And just to show you, this is the aluminum frame that is mounted to the seat support over here, and also at the bottom of the plate using angle brackets. And on the frame there is the tank, the accumulator that has been fitted to the tank being at the highest point. And also at the front we have the pump mount, the pump and the drive system that Nick was talking about earlier. And at the rear we have the motor support, the overhead rack and the manifold. And I'm just going to show you all this on the bike in a minute. And here is some of the pictures for people sitting at the bike who cannot see the bike, but here is the plate that is mounted at the bottom of the bike, which is where the aluminum frame is mounted using these angle brackets. And then on top of the plate is a steel plate which is mounted for the hand pump. And the reason choosing a steel plate over the plate which we had earlier is because the hand pump is used to pump almost close to 600 psi, which requires more pumping on the bike, and using steel will help us make it more rigid and it will be less likely to bend compared to aluminum. And also this is the front drive system that we talked about earlier, which is over here, which is connected to two different gear systems. And also over here is the back rear motor and the motor mount, which is connected to the overhead rack, which eliminates the cantilever position over here. Yeah. And majority of our manufacturing process consists of multiple processes like milling, cutting, welding, and all these processes were done at the Western Machine Shop. And the electrical components that you see on the bike were assembled and tested at the WMU Electronics Lab. And also the main hydraulic system and the assembly of the system for the whole vehicle was done at the WMU Fluids Lab. Here is just some pictures of me doing some milling operation over here. This is the motor mount that is right now on the bike. We were just drilling some holes and cutting it to the dimension using the milling machine. And also it's over here, I'm trying to drill some holes on the overhead rack so that we could mount it on the bike. And then she wants to.
So in conclusion, we were able to build a working bike and it met all the requirements of the competition. Our final weight was 135 pounds. And there's a video of me testing the bike in the hall downstairs. Okay, and also the electrical systems and hydraulic systems were connected and tested. Brakes and shifters were mounted and the bike works. Okay, some things to consider for future teams. The first thing would be lightweight materials. So there's a combination of steel and aluminum on this bike. So if we can find parts, or like we can create parts which are just full aluminum and remove the steel components, that would help the overall weight of the bike. Something else to consider is leak prevention. Right now our hoses which we connect throughout the whole system, they are not custom made. Some of them consist of two hoses connected together, and those connections have leaks which will also cause like pressure loss, and that affects the fluid flow as well. So something else to consider apart from that would also be newer motors and pumps. Right now the pumps and motors we got from the lab downstairs, they are like 4 years old. So there are newer pumps which the future teams could consider to improve on, and weight distribution. As you can see currently, majority of the weight is on the back. So if there's a way to distribute the weight evenly, that would also help the efficiency of the bike. We also want to thank the professors which helped us throughout the process, Dr. Matt, Alin Carl, Dr. Tim Pasang, Dr. Chowdhury, Dr. Jorge, Dana Butt, David Stevenson, Steve Gluck, as well as Mike Conker. They were very helpful throughout the whole process. Thank you.